welcome to another video on calculating enthalpy change. So far we've looked at calculating enthalpy change by using bond enthalpies with known values and then pumping it into an equation and then finding out what delta H is. The next one that we looked at was calorimetry, where we do a practical burning something and then measuring the temperature change to identify how much energy has gone into the water source. And then the next one that we're going to look at is everything is just theoretically calculated by using the equations and the basic recipe around stoichiometry. So for instance, if we look at an equation, C2H5OH, and we're adding that and we're burning it with 3 O2, and that gives you 2 CO2s and 3 H2Os. And that tells you that the delta HR, so the enthalpy change of the reaction, is negative 1235 kilojoules per mole. Okay, so that is the equation that we're going to work with. What does this equation tell us? So first of all, it gives you the recipe of ratios. So we know that 1 mole of ethanol and 3 moles of oxygen react to form 2 moles of carbon dioxide and 3 moles of water. And when we look at this and we follow exactly this recipe and this amount of ratio, this amount of energy will be released. Remember, negative means an exothermic reaction. So this is the amount of energy that gets released when we follow this equation. So the trick now is, the question will be, identify the amount of energy released when we have this as 23 grams. So if 23 grams of ethanol gets burned with oxygen and it produces this, we want to know how much energy is produced. So again, we've done this before when we looked at the ratios and we converted this. So first of all, because we're working grams isn't a standard value in chemistry, so we need to convert this into moles. So that's the first thing that we need to do. And then the second step, after we've done the moles, we need to adjust this whole recipe to get to still be in this amount of this ratio. And because we're readjusting this with the new ratios, we're going to adjust the amount of energy that's also released. So let's have a look at what we do first. So we know that that's the mass. Okay, so the molar mass of that one is going to be 46, and they'll give you this. Okay, so we've got our mass and we've got our molar mass. So the next step is to find out moles. So N equals little 1 over big 1. 23 divided by 46, and that is going to be 0.5, so half a mole. So when we look at this, now we need to readjust this. So if we have half a mole of this, it means that we'll need to change everything and divide everything in half. Okay, so because we originally had 1, now we're changing it to half. This one is also going to be a half. So that's going to be 1.5. That's going to just be 1, and then that one will be 1.5 as well. And if we've done that and we divide this, then it means that half of that ratio or half of that recipe will need to give you half of this amount of energy. So we'll need to divide this as well by 2 to give you that amount of energy. And that is going to be 618 kilojoules per mole. Right, so that's pretty simple. Luckily, because we've done this type of calculation before, it should be easy enough to recognize and to be able to do. So remember, whatever we need to do with one, we'll need to do with everything else. So if we half it, the first one that we're focusing on, if we half this, then we need to half the whole thing plus the amount of energy that is from the base recipe. Okay, so that is pretty straightforward. The molar mass will be given to you. The mass, they'll ask you for a certain amount of mass, what is the amount of energy that gets produced. So yeah, that's what you need to do. So remember your N equals M divided by M calculation, identify how many moles there are, and then adjust the recipe and the amount of energy at the end. And remember, the signs, that negative means it's an exothermic reaction, which means that it will release energy, and a positive is endothermic, so it will absorb energy. Cool, so easy enough.